Hi, if you are measuring the quantity of the macroscopic objects whose mass is relatively larger, then we know that we use the base quantity called mass and its unit is kilograms. But let's say if you are measuring the quantities at the atomic level, at a microscopic level, then we don't opt the kilograms. Just for our convenience, we adopt another unit that is atomic mass unit. So AMU. So, what is a standard definition of AMU? Or so in this question, we are dealing that thing actually. So, in this diagram, you see, one side of the balance we have a carbon, and on the other side we have a argon. So, argon is almost 3.3 times heavier. So, which is basically 39.9 U. So, U is an atomic mass unit, which we also write like this. So, for all elements in a periodic table, we compare their mass in comparison to the carbon neutral atom. So, if I will place magnesium in the place of argon, then the magnesium is two times more heavier than carbon. So, carbon have a 12U and magnesium has a 24U. So we compare the mass of every neutral atom of periodic table in comparison of the carbon. So that's why the option A must be correct, that atomic mass unit is 1/12 of the mass of neutral carbon atom. Hi, this IB Physics past paper MCQ is about nuclear fission reaction. You know that it is a process in which the one heavy unstable nuclide, when it absorbs a neutron, it splits into the two lighter nuclide, which are relatively more stable. But I will give you the explanation of this. And in fact, this question is addressing about the binding energy per nucleon and the binding energy of these fragments and that unstable nuclide. So I will explain you not only theoretically but also from the graph. So let us see. So according to this question, this is that neutron when it hits the nuclide X, it splits into the relatively smaller in size, these two nuclides, whereas the two neutrons are emitted. Now, in the question, in a real question, it is just symbolically like these letters are assigned, but in reality we have a one prominent example of nuclear fission reaction of uranium. I want to mention you that reaction, and that is when a neutron collides with a uranium 92 235, it splits into the two fragments, which the one is xenon, that is 144 and 54, and the other one is a strontium, that is 38 and 90, plus the two neutrons are released, just like you see in this reaction. And don't forget to write the energy is also released during this reaction. So energy is released. Now, in our question, we have to examine, we have to see that binding energy per nucleon of Y, okay, which is the resultant, right, divided by the binding energy per nucleon of X, which is a parent element. So we have to find, is it greater than one or the less than one. And second point is, we have to see if we add the binding energies of Y plus the binding energy of the Z, and we divide it with the binding energy of X, is this greater than one or less than one? Let us see. Now, first of all, I will explain you that why the Y and Z are relatively more stable. The reason is that the reason is they are smaller in size. So if they are smaller in size, then what does it mean? It means that within those nuclides of Y and Z, the strong nuclear force, the force which is responsible to bind the protons and neutrons, that overcome the repulsion between the same charges, same protons, this strong nuclear force comparably more dominant, more powerful than in the X. So that's why we should say that the Y and Z are more stable. Okay, and I will show you exactly this thing. Then X. I will show you exactly this thing from the binding energy per nucleon graph, which is very important because binding energy per nucleon is a factor, a decisive factor, which determines the stability of nuclide. It is not a binding energy, it's binding energy per nucleon. So if we see that this, I'm going to draw this roughly, this graph is something like this, right? So in this binding energy per nucleon graph, the top element that is a most stable is always an iron, right? But we are right now talking about the general. So let's say this is a X, okay, because you know that it has a largest nucleon number because it is converting into the Y and Z. It is producing. So if this is a X, then the Y and Z must have a less nucleon number. So, dear students, you can assume, like, for example, this is Y and this is Z. Okay. Like they should be close to each other. So obviously they will have the less nucleon number, right? So on this basis, don't you think that the binding energy of the Y is obviously per nucleon? I'm saying per nucleon for Y is obviously more than the binding energy per nucleon for X. What we see here is exactly that thing. So if the binding energy of the Y is more, then it means that it should be one greater than one because it is more. Now, let's come to the second part. We know that the energy is released, and that is the energy which is released. So, how that energy is released? That energy is always released whenever this nuclear fission reaction takes place. Certain amount of mass of the X will be lost, and that will convert into the equivalent amount of energy which is released during the reaction. It means that the mass of X is more than the combined mass of Y and Z. So remember here, I'm talking about the nuclear mass of X is more than the sum of nuclear mass of Y and Z because the difference of that mass is converted into the energy. So which means that the binding energy of X, because it's a heavy element, it's more than the sum of the binding energy of Y plus the binding energy of Z. It means that if we take the ratio, so that ratio should be more than 1. My mistake, less than 1, obviously, because it is more. So option C is the right answer for this MCQ. Hello, this IB Physics past paper MCQ is about the thermal energy transfer. So you know that there are the three modes of transfer of heat, which I have shown you on the site. The one is the first is, you see, the conduction, in which the heat, the thermal energy is transferred by a physical contact between the two objects. And the second one is a convection, in which the heat is transferred by the moving fluid. For example, in this diagram, you see that this hot water is circulating, it is going up, cold water is going down. So this is what we can say is the convection. And the third is a radiation, which by which the energy is radiated by the electromagnetic waves, by EM waves. And you know that in the electromagnetic spectrum there are a lot of lights. The one that is prominent is infrared, which carries this thermal energy. Now the question is, if you place the hot piece of rock on a surface of moon with no atmosphere, then which one of these three mode of heat transfer the energy will be transferred? So first of all, the we know that there is a connection, there is a contact between this stone and the moon surface, so the heat will transferred by the conduction, obviously, in all the directions possible, right? So it means that conduction is obviously one of the options. Okay, it is correct. Third thing is, the second thing is, there will be the radiation. Okay, because the electromagnetic radiations can be radiated through the space. It can move through the vacuum, with the speed of light. Okay, they have a different speed, they have a different energy depending on their wavelength, but this heat can be transferred into the without any atmosphere, which means that this heat will be transferred via the long waves infrared primarily. Means that all the EM waves will be emitted, but the IR, the infrared, will carry the most of the energy according to the Stefan Boltzmann law. The third thing is convection will not happen because there is a no moving air, there is a no fluid, or we can say there is a no atmosphere. So there will be no convection take place. So option B is the right answer, which says that the conduction means the one and the radiation only. Let's say if there are the two distant planets where the life is 100% impossible, and I have to compare while living here on Earth, I have to compare which one of them is hotter by just seeing it. This question is going to address this thing. So let's say these are the two planets, planet X and planet Y. What question says that the planet X is less hotter, and by the way, both are the black body radiators. Black body radiators means their emissivity is one, and it means that all the energy that these two absorbs, they radiate all of them. This is what it means, black body radiation. So it means that both of these planets are emitting, releasing, radiating all of their energy in the form of radiations, and we are given the intensity and wavelength curve by in these options. So, and according to the question, the planet X is less hotter and the Y is more hotter, means the Y temperature is more. So the Ty is more than Tx. Well, first of all, I will explain you what the intensity and wavelength graph tells us. According to the Stefan Boltzmann law, and according to the modern physics, that all the energy that is radiated from the planet is not radiated in a form of single wavelength, it is radiated in the entire electromagnetic spectrum, and which you can see easily by looking the different wavelengths. And what is special is that this wavelength, which according to this graph has a maximum intensity, I will call it maximum wavelength. Why? Because this is that specific wavelength of light which carries the maximum portion of energy released from the planet. And just last thing, the area under the graph tells us more interesting thing, and it tells us that how much energy overall is radiated from the planet. So if a one planet have a higher temperature, so obviously its area must be larger because it will radiate more energy, and that is actually we know that the power is proportional to the temperature is power 4 according to the Stefan Boltzmann law, or you can also say luminosity is proportional to the T raised power 4. And now, if I connect this intensity wavelength graph with the planet situation, then remember that this planet is going to release the minimum wavelength, means the gamma ray, to the maximum wavelength electromagnetic, which is a radio wave and also visible light. And for this reason, I'm going to show you all of them to you. So this was just possible for me. So I have tried to show you that whole electromagnetic spectrum is radiated from both of the planets. Now, according to the question, they say the planet X is less hotter, and the graph is actually shown by the dotted for X. You see that the dotted means that in all of these options, this dotted curve is actually representing the intensity wavelength curve for the planet X. And what will be for the planet Y? Let's take advantage of Wien's law. So what the Wien's law says that it relates the temperature and the wavelength. Which wavelength? The maximum wavelength, which I mentioned you here. The maximum wavelength doesn't mean it has a maximum length. No, means that it is that light which carries the maximum energy. So it says that the product of the temperature and the maximum wavelength is constant, and that constant is 2.9 times 10 to the power negative 3 meter Kelvin. So that is constant. It means that the maximum wavelength and the temperature is inversely proportional. So, like this. So, if you use this information, what information that we know that the temperature for the x is less than temperature for the y, which means that now logically we can derive the result that the maximum wavelength emitted for the x would be larger than the maximum wavelength for the y. It means that, so dear students, let's apply now the results that we have learned. Now I'm going to compare the two. So I'm saying, let's say this is the graph for the x, and this is the wavelength for the x, lambda x. Now, what we have learned that the wavelength of X must be larger. So it, and secondly, the temperature of Y is more. That's why the planet Y must release more energy. So it should have a more area under the curve. So which directly leads what, where it does it lead to? Don't you think it leads to exactly something like this curve? Because if you see that the area under this curve is first of all more than the area under the curve for the x, which means more energy is released. And secondly, dear students, you can compare the wavelength for the y is obviously more less than the wavelength for the x. So it means that this is for the y, and you can easily identify which one should be our right answer. So none other than option D is the only possible right answer for this question. Hi, this question is about albedo. So if the average albedo according to the question is of glacier ice 0.25, by the way, it means that the 25% of any intensity of light that is incident on glacier is reflected. Okay. So if it is reflected, then 75% of that intensity is absorbed. So I will give you the little background of the power, and also that if our sun is so hot that its core temperature is 15 million degrees Celsius, its surface temperature is 5500 degrees Celsius, then why does not it burn the earth? Okay. So what actually happens when the intensity of the light of sun that is incident, if it is I, so how much is reflected? So 25% is straight reflected, which means it is 0.25 I. And then how much is absorbed? So let's find out. It should be 0.75. So 0.75 I, okay, or the power P divided by 0.25 of incident power. Remember that I'm saying incident power, right? So this is incident power. It's not the, it's a 75% of incident power. So you can easily calculate it. It should be 3. So right answer is option D, but please stay in a video and see what happens. So if 25% is reflected, then what happens with the rest of that? The rest of that is radiated in a majorly in a form of infrared, but all of that will be radiated if we consider it a black body radiation, but it is of course not. So some part of absorbed power is radiated. Now when the sun radiates a lot of energy, so what happens, this energy is coming directly on the surface of earth. So what I'm considering that all of the light that incident on earth is not eventually incident on the surface of earth. Just one fourth of the area of earth absorbs that light. Okay, just one fourth. And and further, that light, a part of that light is reflected, and this is absorbed. So that absorbed power actually rises the temperature of the surface of earth. So I hope you understand. In case of any question, let me know in comments. Bye. If you perform the same experiment, that is measuring the time period of simple pendulum on the two different planets like Earth and Mercury, then the time period of the pendulum is different on both places. And what thing that affects it, that thing is gravitational field strength. That is the strength of its gravity of planet. So in this question, we will try to find out the time period of pendulum on Mercury if its time period on Earth is T. And T means that the time period is T is equals to 2 pi square root of length of pendulum divided by gravitational field strength, so GE. So we are provided the information that the gravitational field strength on Mercury is zero point 0.4 g, means 40% of what we have on Earth or near the surface of Earth. Not only that, we will try to find it, but also I will explain you why the simple pendulum gets faster or gets slowed down on Mercury in the end of the video. So let's say this is a path of its trajectory, so which it is moving in a circular path, by the way, and this is a equilibrium position where its displacement is zero, as you know that according to the SHM concept, and its time period is 2 pi L over G. Let's find out that what time that it takes to complete one cycle. Means what is one cycle on Mercury? It will go to the other extreme position and then back to its original position. What time does it take? So we know that the time period on the Mercury, let's say Tm, is equals to 2 pi square root of the same length divided by the gravitational field strength on Mercury. Now, we will write here, we will plug the value of the gravitational field strength in terms of the gravitational field strength of Earth, which is zero point 0.4 times GE. And you can write 1 over zero point 0.4 like, why not we can write 10 over 4, or yes, so 10 over 4 L over GE. And then we can take the square root of 10 over 4 outside, and inside what we have remaining is the time period of the pendulum on the Earth, which is described in this question by the letter T. So this square root of 10 over 4 is telling us that the time period of simple pendulum on Mercury is obviously more. So it means that this pendulum will get slow, and I find it. So its exact answer is 1.58. So which we can round off to 1.6 t, and that's why our right answer for this question is option C, which is 1.6 times t. Now, don't go anywhere. I'm going to tell you that why does it slow down in terms of forces. And for this, we must draw, first of all, free body diagram. So this is our rectangular coordinate system. So you know that either it is on the Earth or on a Mercury, there are the two forces, and we can draw them here. So let's say this is a force applied by the Earth. So this is mg. And there's another force that is a force of tension. So this is a force of tension. So if you make a components of mg, so dear students, there are the two components. So the one component is in this direction, and the other component is perpendicular to this. So this is theta, since this is mg cos theta, which is going to cancel or balance with the force of tension, and this is mg sin theta. Now, important thing is this force of mg sin theta is the one that is pulling the object towards the equilibrium position. So now see one thing, I am going to show you a longer arrow for the Earth, because for the Earth that component is more, so mg sin theta. But for the Mercury, that component is smaller, so it is zero point 0.4. So this force, the force that is pulling towards the center, towards the equilibrium position, is less on Mercury. That's why it will get slow, because it is not pulled that harder towards the equilibrium position. So it will complete its cycle, but it will take more time because force pulling towards equilibrium position is small. So I hope you get the idea. No coherence, no fringes. So let's unlock the most important as well as puzzling condition of the interference of the two waves. So in this question, we are going to discuss if the two waves have to be coherent in order to produce fringes, then what factors make those two waves coherent? So let us investigate. I will completely show you comprehensively by drawing the wave, and I will show you that if the two waves are coherent, then not only it means that their frequency is constant, but also it means that their phase difference is also constant. If you take at any point and you calculate the phase difference at any given point, you will get a same value, which makes the two waves coherent and they are able to interfere. So constant phase difference. So it means that its answer should be the frequency should be same and the phase difference should be constant. But let us see. So for example, if the two waves are, if the basically the one monochromatic wave, and I'm showing you the wavefronts and the distance between them is a one wavelength, is passing through the two slits. So the two by passing through the two slits, these waves will be diffracting without any change in their wavelength. So when it will diffract, so you see that these two waves which are monochromatic are interfering with one another at some given points, at these given points. At some points, they will do interfere constructively, and at some point, they will interfere destructively. And hence, what pattern do we get? We always get a bright spot due to the constructive interference in the middle, and then we get a dark spot due to destructive interference. Anyways, these are the overall generally idea of the fringes. Between any two consecutive bright fringes, we have a dark fringe that is also called minima. Now, dear students, understand this idea concept that these two wavefronts, which are passing through the two slits, these wavefronts, they have a same wavelength. They will maintain the same wavelength between them. So this is also the lambda, just like this is a lambda wavelength. So it means it is monochromatic. So which means that if the wavelength has not changed, it means the frequency is obviously will remain same. So in that way, they will interfere with one another. But this point is tricky. That what is an exact mean of phase difference is constant, that I will going to show you exactly in this section. Not only that, I will also explain you the path difference. So let's draw the first wave. So that is going to be like this. This is a one wave that is going to interfere with another wave. As I told you that they have a same wavelength, which means they have a same frequency, like this. Now notice that their path difference is zero, which means that they will interfere constructively, and you see that their crust and crust overlap with one another, as well as the trough and trough. Now let's talk about the phase difference, which is important in our case. So this is 0 degrees, this is pi, this is 2 pi radians, and then this is 3 pi radians. And in the same manner, we have here the pi, here we have a 2 pi, and here we have a 3 pi. So if, for an example, you take a phase difference between these 2 points, so what is that phase difference? So phase difference will be 0, and that will remain 0 at all the points at any given point on the two waves. Even if you take a phase difference at that point. So the phase difference, what is a phase at that point? It is obviously we have 1.5 pi. Here we have a 1.5 pi. So when you will take a difference, we will have once again 0 phase difference. But let's say if there's another wave, although the two waves have a same frequency, but I am taking intentionally, I'm going to start this wave from here. So now I'm intentionally producing a phase difference because I want to show you that it is not necessary that the two waves which are producing a constructive interference will always have a phase difference 0. It is not necessary. Why? Because if you consider this point, this is 0. For this wave, it is pi, this is 2 pi, this is 3 pi, and this is 4 pi. Now compare the first wave with the third, this wave. I'm going to consider the interference between these two waves. So now notice, this is pi and this is 3 pi. Take the difference of these two. So when you will take a difference of these two, so what is answer? 2 pi. Now take a difference of any other. What about 2 pi and 4 pi? Take a difference of these two phases. So you will once again get the same answer, 2 pi. And it will remain as it is. But if this wave will not have a constant frequency, which means that it is something like this. Okay, now the phase difference will obviously change. It means that it is important that the phase difference must be constant. That makes the two waves a wave coherent. Last but not least, kindly consider the interference between these two waves, the wave 1 and the wave number 4. Because in these two waves will produce a destructive interference and hence produce a minima or a dark spot on a double slit interference pattern. So what do we see in this case, dear students? So this is 0, this is pi. So now kindly see, once again, see this point. This is pi, and corresponding point for this wave, the angle is 4 pi. So if we take a difference between the 4 pi and pi, so it is 3 pi. It means that at all the points, the phase difference must be pi, and we see exactly, yes, it is true what we see from here. And secondly, kindly notice the path difference. The path difference is 1.5 pi, means 3 pi over 2, which is a condition for a destructive interference. So these conditions and all of the information, I hope, is useful for you to understand now what factors make the two waves coherent so they can interfere and produce constructive and destructive interference. The one is a frequency must be constant, same, and the phase difference must be constant as well. Two Doppler shifts in a one single echo. How do you find the frequency of the sound that catches up to the very train that made it? So this question is about the Doppler shift. So what we see in a question, that a train that is moving with a constant speed u towards a cliff that is stationary in front of that. Since this the whistle is produced by the train, and the train is moving with the speed u, so that's why this is our moving source. That's why I have given it a name, source moving towards observer. And in this scenario, this cliff that is in front of that, this stationary cliff is acting as an observer, which is stationary. So a sound that is traveling from a train to the cliff will bounce back from the cliff. And in this way, both will switch their roles. So in that case, in this situation, now the cliff will act as a source and the train will act as an observer. So how do you find the frequency in that case? That's what we are going to solve today. So if this is a train that is moving towards a cliff, and just suppose that this is a wave that is sent by the train, and this is a wave that is going to hit the cliff. So I'm going to show you the next position of the train, and you will see that there will be a Doppler shift in this wave. And that's why there will be a change in frequency that we are going to calculate very soon. So you see that a wave is compressed because the train is moving with a constant speed towards it. So if you want to know what is a frequency, so I am saying that this is a frequency received by an observer, which in this case is a cliff, that is equals to V over V. What we should write, because the source is moving towards the observer, so frequency should increase. So you should write negative sign here. We should subtract the two velocities, because in this case the relative velocity is V minus U into F, and according to our data booklet. Now we will write here the values according to our question. The train speed is C. So the train speed is u, and we are going to put the values. So the speed of the sound is c divided by c minus u into the frequency. This is the original frequency of the sound that is produced by the train. So this is f prime is a frequency that is received by the cliff. So another thing, look at this. I'm showing you the wavefronts, that how these wavefronts are compressed towards the observer. So this is a source. These compressed wavefront shows us that because the distance between any two consecutive wavefront is showing a wavelength. So you see on this side the wavelength is decreasing. That is a Doppler shift. And on this side the wavelength is increasing. So this becomes when the source moves in this direction. So anyways, now in this second scenario, when the source will become observer, so I mean to say now the train is receiving a sound from the observer. So this is source now, because it is reflecting the sound wave, because sound is a wave, so it is reflected with the same speed according to the question. So the speed of the sound is c, whereas the train is still moving with the same speed u. So there will be once again another Doppler shift. And in this echo, I told you already in the beginning of the video, there will be the two Doppler shifts in a single echo. So what is a frequency that is received by the train? So let's call it f prime. Okay. So now in this case, we can take a scenario of the Doppler effect in which the source is at rest and the observer is moving towards a source, because in this case this is an observer and the train is an observer and it is moving towards a source. So I'm saying it is an observer which is moving towards source. So if you remember, what is the equation mentioned in your data booklet for IB physics? So that is, this is an observed frequency or apparent frequency that is equals to V plus U. I'm going to write this addition of the two velocities because this is a relative velocity divided by V. And here the V represents the speed of the sound, whereas the U represents, generally speaking, the speed of an observer times the frequency uh, of the actual frequency. Now, if we synchronize this equation according to our question, then dear students, this is what we need to calculate. This is the frequency f double prime, which is received by the train, is equals to the v is the speed of the sound, that is c according to the question, plus u divided by c into this f is a frequency of this sound, which is, if you remember, it's a f prime, which we have seen in a previous case. So let's plug the value of f prime here, and we will get finally the expression that is required. So c plus u over c into f prime. Now the f prime was, if you remember, is c over c minus u times the f. The f is the actual frequency of the sound whistle that is produced by the train. And you can see that the c and this c is cancelled out. And finally, the option A is the right answer for this past paper question about the Doppler effect. As you travel from the zero potential to the positive potential, one electrostatic physical quantity stays perfectly constant, while another electrostatic physical quantity steadily and uniformly changes. Let us investigate in this question. So I have given you, this is a diagram given us in the question. So let us say if this is a charge that is going from a 0 volt to some higher potential V, and it is going, by any means we are transferring it from this point to another point. So how does the potential changes and how does the electric field changes, or does it stay as constant? Let us investigate. So whenever we produce a potential difference between the two plates by connecting the two parallel plates with a battery, so let's say the one plate develops a higher potential and another plate develops a lower potential comparatively. Now for the parallel plates, the field between them is uniform. And how do we represent this uniform field? We represent it with the help of these parallel lines. Okay. And why parallel lines? Because the field is constant irrespective of the position of a charge. Whatever point you take between the plates, either that point is close to this plate or the point is close to this plate. At both of these points, the electric field is constant. Now, we will debate about the reasons. Now, why the electric field strength is constant? Because the important reason is same electrostatic force is applied at both positions on the charge, right? Can I say E is equals to, since according to its definition it's electric field strength, so it's the electrostatic force applied per unit charge. Secondly, don't forget that electric field strength is a vector quantity and it is directed from a positive to the negative plate. So, since its direction is not changing and a vector can change even if its magnitude is constant, but if its direction is changing, then this factor can make it non uniform. And exactly what we observe. Dear students, we observe this thing over here on the edges of the plates where the field lines are not uniform, they are not aligned. So that's why electric field is also non-uniform, because electric field's direction is changing at every point. That was my point. So electric field strength is constant between the plates. Okay, so this is a first reason. And the second reason is, dear students, now if you look at these parallel plates, where if I try to show you that actually how the electric potential changes from 0 volt to the maximum value, because this electric potential is the work done per unit charge. So as you move the charge from a zero potential to the maximum potential, this work done increases, means the energy stored in the charge increases if it is a positive charge. So I can show you exactly in the middle, when the distance between the initial point and that point is, let's say, the x over 2, whereas the x is a total distance between the two plates. So exactly at that point, dear students, the potential is half of its value. So it means that, so if I try to find out the E, which is equals to V over D, generally speaking, according to your IB data booklet. So if you apply this equation, so in the middle, since the potential is half and the distance is half as well, so that's why the electric field strength is still same. So you can take at any point. If I draw another equipotential surface at that point, the distance from this to this point is 2x over 3, means 2 2/3 of that. So the potential will be equals to 2v over 3. Once again, if you take a ratio, that will remain same. So it means that if E is constant, so if E is constant, which means that the V is proportional to X. Okay, so just the last thing I want to show you the results in a graph. So the electric field strength does not change, it is constant if the all the lines are parallel. And secondly, the potential changes uniformly. So I'm trying this graph, but remember, I am just showing you the magnitudes. I'm not relating the negative sign in electric field strength formula, which relates with electric potential. This video is generally for both HL and SL students. So the potential is proportional to X and electric field strength is constant. Okay, so the right answer is option B, which says these two things. Launch a heavy satellite deep into the space until its distance becomes from the center of the earth becomes double, and then watch is the crushing grip of gravity on the satellite weakens dramatically and the gravitational potential energy shifts to the brand new state or not. So this is what we are going to see in this question, that what happens to the force of gravity and the potential energy when you take a satellite from a surface of earth to that point where its distance is double of the radius of the earth. So first of all, I'm going to show you the
the visual gravitational field lines. These are the field lines which show us the strength of the gravity of the planet. So if a planet is a larger in size, then there will be more lines we have to show, we have to depict more lines. So anyways, this is the visual representation of the gravity of the planet. And all the field lines are towards the center, showing us that the Earth or the planet pulls any object, even if it's satellite or anything, towards its center. So right now, this is a radius of the Earth, and the satellite was initially at the surface, which we where we have taken it to that point where its distance is 2r. So dear students, this is a new position of the satellite, and I'm just for a reference, I'm going to show you the orbit of the satellite at that point, and this is a orbit. Now speed will be obviously changed, time period will change. When it was orbiting very close to the Earth, it will have a different time period. What is the weight, what is the force of gravity right at that point? With what force the Earth is still pulling it towards the center? That's what we have to calculate. So let's find it. So the weight is actually the pull of the Earth, and the weight is, that's why the according to the Newton's law of gravitation, this is equals to the G. Big M is the mass of the planet, small m is the mass of the satellite, divided by the r square. R is the orbital distance. Now, in this equation, this Gm over r square is showing us the gravitational field strength. That's why we usually write the weight like this equation as well. Anyways, we are going to use this equation. So the weight is equals to mass of the planet have not changed, neither the satellite, divided by distance is 2r, is basically 2 big R and take its square. So this is going to become gmm over 4r square, and that you can write it like this, 1 over 4 into. So students, this is a weight, it's this is a new force of gravity at that point, and you can see it is 0.25 times the force of gravity, or 0.25 times the weight of the satellite at close to the surface of the Earth. So that's why we should select 0.25 W. And this is a force that was applied by the Earth on the satellite when it was close. Now, let's talk about the gravitational potential energy. And the interesting part of this video is that I am going to show you the graph as well. So don't skip the video. Now, when the satellite is orbiting, it will have a certain speed at that point. It will have a total energy, it will have a kinetic energy as well as potential energy. Now, the potential energy, EP, is equals to the negative gmm over small r. Now, dear students, why it is negative? Because of the attraction. Because you have to deliver the energy to the satellite to move it away from the Earth. That's why it's negative. So you have to addition the energy into the system in order to take it away. So all the attractive forces are negative. So, anyways, I'm going to right here the capital R when it was close to the surface of the Earth, and the new potential energy when it will be at that point will be Tmm over 2r. So you can see that it has become one half of the previous amount of energy, which means that it has become a less negative than initially. What does it mean? It means that less negative means that actually the potential energy has increased, because if you take a difference of the energy between these 2 points, it will be positive, which shows the energy has increased. Dear students, it is not asked, but I'm just showing you for the reference, and its answer is positive. Okay, because I have subtracted the final minus initial, so you can see that this is an energy that has been increased. Anyways, now I'm going to show you quickly the graph. Okay, so dear students, at that point, it is maximum negative, which is at a surface of Earth, negative gmm over r. So this always follow this pattern, and you see that as the distance is increasing, it is becoming less negative. So at a distance 2r, it is zero point 0.5 times EP. and then further you can see how it is decreasing. So it means that this is obviously this should be the right answer. So right answer is option C, which is 0.25 W and 0.50 EP.
Electric fields and the other fields are completely invisible. For this reason, IB examiners they always love to give this type of questions where you have to compute and determine the position where the field strength is maximum or minimum. So in this question, as you see, we are given the two charges, neg 5 microcoulomb and negative 2.5 microcoulomb. Both are static charges, so both will create their own electric field strength. So we have to determine that what at what position a, B, C, or D among all of these where the field strength is maximum. So it is not difficult. It is very easy. But the main thing for which you should not skip the video is we will calculate the electric field strength in terms of E. So you see here that we will try to find out the direction as well as their magnitude separately for all of the options. So let's start with the A. We know that electric field due to the positive charge is always away from the charge. So when I will try to draw a vector due to this positive charge, so I must draw a sign that represents the electric field strength vector away from that. And since this is a negative charge, so its electric field strength should be towards because field is towards, right? So obviously you see that the two vectors are in opposite direction. That gives us a least possibility that it may have a maximum strength of the magnetic field. So it should not be A. Let's check the option B. Now for the option B, since it lies exactly with between the positive and negative charges, where the electric field has its maximum strength because the field is in a form of straight line almost and it is uniform in the middle. So it should be maximum at the B. So this is the direction. This is the electric field due to the positive charge that is away from the charge, and this is the electric field due to the negative charge that is towards the negative charge. And you see that the two vectors add up and they must give us a maximum strength. Okay, now let's check the option C. Now for the option C, if you notice that from the positive charge the electric field should be directed away, right? And due to the negative charge it is towards. So it is giving us a situation in which the two vectors are not giving either a maximum value nor minimum value, but it is surety that C is also not an option because they are not giving us a maximum answer. Now what about the D? Now for the D, due to the positive charge it will be away, but it will have a less value because D point is distant from that positive charge, whereas for the negative charge it is towards. So it is again, you see the two vectors are in opposite direction. So only the right answer should be option B. But important part of the video is starting now because I'm going to calculate in terms of E. So let's calculate, but look at one thing, that it is not a coincidence. They have intentionally given us in such a way that all the points from the charges are at the same distance, right? This distance and this distance is equal. This distance is also equal. All right. So it means that if I imagine that, let's say, if I say this distance is D, the point C is at distance D from the negative charge, and so at that point, the direction of electric field is towards the negative charge due to the negative charge, and its magnitude should be E is equals to KQ. Remember, I'm writing the magnitude. I'm not using negative sign. KQ over D square. Okay. It means that when I will talk about this distance is d as well. But now this time, due to this positive charge, which is two times more in magnitude than the negative charge, so don't you think that at that point it must produce an electric field two times of E? Okay, because it is K into 2Q over D square. So that should give us 2E. Okay, so if you understand this thing, now we are ready and we can start one by one from the option.
So positive charge is at a distance d, whereas the negative charge, can I say it's at a distance 3d? You can see the question that it is a distance 3d. This d, this d, as well as this d, right? So it means that we have already computed that due to the positive charge, this electric field strength has a magnitude 2e. So what about this electric field due to the negative charge? So we can quickly calculate it. It should be equals to K into Q, because it's a negative charge, magnitude is Q. So over 3T whole square. So that should be equals to KQ over 90 square. That should give us E over 9, right? So which means that if it is E over 9, then these two vectors are in opposite direction. So that's why the net magnetic field strength must be 2E minus E over 9. So which gives us, dear students, 17E over 9 is the net electric field strength at the position A. Okay, now let's talk about the B. Now, I told you that for the option B, since the two fields are in same direction, so they must give us the maximum value. And whereas you know that this distance is D, whereas this distance is also D, right? So so if you remember, we have already calculated due to the positive charge, it is 2e. So that I'm going to draw here. Due to the positive charge, it is 2e. Then due to the negative charge, which is half of its magnitude, right? Negative 2.5. So it should be just E, right? Because its charge is half, whereas the distance is same from both charges. So it is E. So don't you think the net magnetic field strength is equals to 3E? That should be a maximum answer. Now, I hope you understand the pattern. I'm just going to show you the rest of the thing. So you can see that due to the positive charge, the electric field at the position D is just 2E over 9. I have put the value 2Q and the distance 3D and took its square. Whereas due to the negative charge, it should be E, right? Which you know that. So so it is, so at D it is 7E over 9, which is also less than 3E. And at the option at the point D, you don't need to calculate, because I told you that these two vectors are not in same line. So it cannot give you the maximum. So the option B is the right answer. Last but not least, kindly note down I have calculated electric field strength due to the both charges. So you can see it is not giving us a maximum value. Hi, this question is about the AC and DC current alternating current, which is not included in our new syllabus. So you can skip it. In this question, we have to identify the units of these two physical quantities, and but I will give you a little introduction that what is the meaning of this quantity. So first of all, the magnetic flux. So flux means the flow, the flow of something. So when we talk about the magnetic flux, it means that, so it's a flow of the magnetic field lines through the certain surface area. So let's say if in this example I just show you the three lines which are crossing, and in the next, the same flat surface, we see there are more number of lines crossing that certain surface area. So which means this surface has a more flux because more lines are crossing through it. So we always measure it in the Weber, so which is PA. So Weber is the unit of the magnetic flux. Now, magnetic field strength, we have to identify a unit of magnetic field strength irrelevant of the flux, means that that is generally its unit is Tesla, which is equals to Newton per ampere per meter. But if you put the same surface in the magnetic field, so you can see that when you will put the surface here, the more lines are passing through the surface. But when you will place this surface over here, so less number of lines are passing through it. That's why we also say that the field strength is equals to the flux crossed through the surface per unit area. But remember, we will identify the Tesla as a unit of field strength, uh, because it is not necessary that the magnetic field is present, so flux will be also present, right? So flux is also whenever it cuts the certain surface, then flux is produced. That's why you have to identify Tesla, not the Weber per meter square. So the right answer for this question is option B, which says that Weber for flux and Tesla for the field strength. Hi, this question from the May 2017 time zone 1 is not included because any question related to capacitor, either energy stored in a capacitor or the charge of a capacitor, any question related to capacitor is not a part of our new IB syllabus. So you can skip this question. Hi, once again, this question number 35 from this exam year and time zone 1 is not included because it is about the charging of a capacitor. So, charging, discharging, energy stored, all of that are not included clearly. So, you can skip. Hi, is this the magnetic field crushing this coil inward or ripping it apart outward? Let's find out in this question. So, we are giving a scenario that this is a coil which is placed in a uniform magnetic field. Now, when we say the uniform magnetic field going into the page, so actually it means that all of the field is going in a negative z direction if you call it negative z axis. So this is a direction of the magnetic field. So right now the maximum flux is produced because all the lines are perpendicular to the surface. So and secondly, this coil is carrying a current which is a clockwise. So clockwise means that this current is flowing in this direction like this. So we know that whenever a coil or a wire carries the current in a magnetic field, and if it is placed perpendicular, then there is always a maximum force exerted by the magnetic field. And why is that? Please understand that when you place a coil or a wire in a magnetic field, so actually the two fields interact. What two fields? The one field that is called external field, which is going into the plane, and secondly the field that is produced by the coil itself. So if these two fields are interacting and they are opposing each other, they are canceling out each other, that determines the direction. So and we use obviously the Fleming left hand rule to find the direction. So this is the Fleming rule. So according to this rule, this arrow is always represent the magnetic force. This is the magnetic field strength, and this is the current. So FPI rule, and the angle between all of them is 90 degrees. So we will apply this rule on this coil, and exactly if the current is flowing in this direction, then what is a force? So you can align FPI. So you can align this finger, this is my left hand, this finger is representing the direction of current, this is representing the direction of magnetic field which is going into the plane, and you can see my thumb is pointing downward, which is clearly showing us that the answer should be the option D, which means that the force exerted on this segment of the coil is downward. But our video is not ending here because interesting part is coming. So I will show you more conceptually that why it is downward. But first of all, according to the Fleming rule, you can see that the current flowing in that part of is this is representing the current's direction, and this represents the direction of the magnetic field strength. So the force is perpendicular to the both of them. So this is the force. Now, please come on this part where I'm going to show you the direction of the current in this coil, which is going in this direction. So imagine it is a piece of wire which carries a current to the left, my left. Okay. So if I apply the right hand grip rule, pointing my thumb in the direction of current, so I see the curling fingers are showing the direction of current. So on the upper side of the wire, the fingers are going into the plane, and on the lower side, the fingers are coming out of the plane. So I can draw here the magnetic field of the wire like this: cross, 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 cross on the upper side, and dots on the lower side, which represents the magnetic field of the wire. Now, what is the direction of the external field? Dear students, external field's direction is into the plane at all the positions. So don't you think there's a one area where the two fields are opposing each other, they are canceling out each other, weakening each other, right? And that is easy to guess, obviously, on the lower part, where the one field is going into the plane and the one field is coming out of the plane, and both are canceling out each other, and hence you have a strong field on the upper part and the weak field relatively this part. That's why the force is exerted downward. Okay, just last but not least, what will be what will happen to the coil? Well, if we draw the free body diagram of a coil, nothing will happen to the coil, because if I represent the whole coil as a dot, means an object, so the force on this part is upward because current is going in opposite direction than this one. So if the force is applied downward, then on this side the force will be applied upward and equal amount of force. So I can draw this arrow, and on the lower part this arrow is down. On the right hand side, I mean this part, the you can draw like this: FBI. So current is going down, so the force is exerted in this direction on this part, and on the other part, this part, the force will be obviously in opposite direction. So these are all forces are in same magnitude and in opposite direction, so hence the F net is 0. So neither this coil is crushing inward nor it is ripping it apart outward, so nothing is happening. Most of the students, when they see this atomic sizing nuclear sizing questions, they just use the basic multiplication methods, but they forget that universe does not scale linearly, and neither do the atomic nuclei. So which, for instance, in this question, what is given to us that this is a silver nucleus, and the silver nucleus radius is, because in the question it is mentioned that the diameter of the silver nucleus is 3 times the diameter of that unknown element which we have to identify, we have to find out. So I would say that this is that unknown element, and if its radius is r, then it would be 3r according to the question. So its nucleon number is 108. What is a nucleon number of this unknown element? We have to find out. Either it's a helium, lithium, boron, or neon. Let's find out. Now we have to use here the information that we get from the Rutherford scattering experiment, because that make us capable to calculate and estimate value of the radius of nucleus based on the authentic calculations. So we know that the radius of any nucleus is proportional to the one third of the power of nuclear number. That's why I told you in the start that it does not scale linearly, right? So we are going to use this information. We know that the radius of the silver is 3 times the radius of that unknown nucleus. Now, the radius of the silver can be written as R0, which is Fermi radius, and its value is a constant. It will not be affected. So a nuclear number of the silver raised to power 1 over 3 is equals to 3 times of R0 AX. We don't know the nuclear number raised to power 1 over 3. So we can cancel out this constant on a both sides, and you can turn it into the form of ratio. I mean, you can take this 3 on the other side. Nuclear number of the silver is 108 raised to power 1 over 3 divided by 3 is equals to nuclear number of unknown nucleus raised to power 1 over 3. Now I want to get rid of this 1 over 3. So what if I take the one, I mean the third power on the both sides? If I take a cube on both sides of the equation, get rid of this one third, so it will be like this, right? So I'm going to take, to balance this, I'm going to take cube as well here, right? So it is cancelled out, whereas you can open the bracket and you can take cube in numerator and denominator. So what you will get eventually is 108 raised to power over 3 raised to power 3 is equals to the nuclear number of that unknown radius, and that is 108 over 27, and that is 4. It means that it must be according to Rutherford's estimated radius equation, it must be helium, which means the option A is the right answer. Now see that although the silver have a higher nuclear number, it have a larger number of protons and neutrons in its nucleus, but the helium is relatively very lighter. But you can see that their radiuses are in this format, that the radius of silver is 3 times of the radius of helium, but there's a huge difference in their masses. So the right answer is option A. Hi, this question is about the Heisenberg uncertainty principle, which is not a part of our new syllabus. Hi, what happens when a light physically crashes into the matter like a billiard ball? So, this question actually addresses the particle nature of the light. Now, the two experiments which show this behavior are the Compton effect and the photoelectric effect. So, we will identify not only what happens with the energy and the wavelength of the photon after the collision, but either it's a Compton and or the photoelectric. So, this question categorically mentions about the scattering of of the photon after the collision with a stationary electron. So imagine that this is the photon that have a so much energy, that so that's why I will draw a very small wavelength of that photon, and it is traveling towards an electron which is at rest. So it is stationary. Now, this photon can be only the photon of X rays. And why I'm saying it with so much confidence, because in the photoelectric effect, whenever a light within this range from the infrared to the ultraviolet, and all the visible lights are automatically included in this range. So, any light within this group, when this light shines on a metal surface, so the photon of that light, it ejects one electron at one time. So why this happens? So because all the energy of that photon is completely given to the electron, and the photon vanishes. Photon is no more. It has given 100% of its energy to the electron. That happens in a photoelectric effect. So I'm sure now it is easy to identify that this photon should be of X-ray, because it have a more energy than ultraviolet, and this process is obviously a Compton effect. So the wavelength of this photon is lambda, whereas the energy of this incident photon is EI is equals to hc over lambda. Since the wavelength is so small, that's why the energy of this incident photon is so large. So when it will hit the electron, as you see in the second diagram, right now, what happens, the drastically energy increases of electron, and electron recoils, I mean electron moves in some other direction, like this, according to the Compton effect experiment. So which, whereas photon does not deliver 100% of energy, unlike the photoelectric effect, it scatters. So how does it scatters? It scatter with a longer wavelength. So if it has a longer wavelength, means this is the energy of the scattered photon, which is hc over lambda s. Since you see that the scattered wavelength is more than the incident wavelength, which means that the scattered photon's energy is less than the photon's in incident photon energy. So it is scattered with a less energy, whereas it have a high energy. So what we conclude after this discussion, that energy of the scattered photon must be less than the energy of the incident photon, right? Whereas since the energy is inversely proportional to wavelength, so its wavelength must be greater than the wavelength of incident photon. So that's why the right answer is option D. Hi, this question is about an electron capture, which seems that it is included in our new syllabus, but why it is not? Because it is about the particle physics. The particles like leptons, muons, you have to have a knowledge about it, and it's not included in our syllabus, so you can skip this.